right, next up we're going to be covering our section on linear equations. So we're going to be discussing another method to solve differential equations of a specific type. And similar to with separable equations, our approach is going to be that we learn to manipulate this equation in a special way so that it reduces to a calculus problem where we just integrate both sides. We're going to start off by talking about the format of equations where we can apply this method. So we need to discuss what is a linear equation. So these are going to be first order and, as the name implies, linear equations. And they're going to take on the form a1, a function of x times dy dx, plus a2, a function of x times y, is equal to g of x. That's functions. Similar to in prior sections, when I say a1, a2, and g are functions of x, those can be constant functions. So it could be 1 dy dx plus 2y equals 3. That's still a linear equation even though you don't explicitly see x. We want to be able to rearrange these into the standard form. The reason for this is because this form is related to how the solution is formulated. And that's just going to be dividing by a1. So we're going to have dy dx, plus p of x y is equal to some f of x, where p is a2 over a1 and f is g over a1. So when you set out to solve a linear equation, if it has something multiplying dy dx, divide that through the whole thing before you start the problem. And the reason you need to do that is because it's the format that was in mind when sort of we wrote out the steps to solve it. So if you don't do that, things are going to be kind of off. So that's the type of equation we're looking to solve. And the next thing I wanted to do is sort of try to build intuition for the solutions, or at least show you all how we're going to be getting the solution. If you're taking skeleton notes, it's not a lot to fill in, so go ahead. But if you're taking notes on your own, there's going to be like a lot of lines of derivation, and it might be more meaningful for you to just watch and kind of take it in. Otherwise, if you really want to take the notes freehand, just feel free to pause when you need to. I don't want to linger too much over every step of this. I really just want you to get an idea of how it's working. So make that call for yourself when you need to pause to fill everything in. But building that intuition. So we're going to consider p of x some function. And for this example, we're going to think about p equal to x squared. If we wanted to, we could compute e to integral p dx. So integral x squared is 1/3 x cubed. So e to integral p, for the example I gave you, is e to 1/3 x cubed. If we have that, we can also compute some derivatives. If we wanted to find d dx of e to integral p of x dx times y, we could evaluate that. It looks really intimidating because I've got x's and y's and integrals hanging out, but this really is like a product rule and a chain rule put together. So first my product rule would be derivative of that one. Yeah, okay. So I'm going to keep e to integral p of x dx the same and take derivative of the second. And then I'm going to add taking derivative of the first thing. And multiplying by y. So that right there is a product rule. And then in order to evaluate this derivative right here, I'm going to need a chain rule, sorry. So I'm going to have e to integral p of x dx, dy over dx, plus the chain rule tells me I take derivative of what's inside e, but that's just going to be p, because derivative of an integral is whatever's inside. Integrals are antiderivatives, so derivative and antiderivative cancel each other out. So derivative of what's inside times the integral of e just stays e. So that right there was a chain rule. And I'm about to move to the next page if you need to pause and kind of copy all that down. But now I can go ahead and pull out all together that e that appeared on both terms. I'm just going to pull that out as a common constant. And then I'm left with dy dx from the first part plus p of x times y from the second part. And that's looking a whole lot like my standard form. And originally this had been that it's the derivative with respect to x of e to integral p of x dx times y. And right now I don't really know what I would do with those different parts. I just want you to see that somehow the special e to integral p relates one derivative to the standard form of our differential equation. And since that can be a little bit abstract to see with all the x's, I also wanted to put in the example real quick. So if I'm looking at that e to 1/3 x cubed times y, if I want to compute this derivative, I take e as it is, and I take dy dx, and then I take derivative of e to 1/3 x cubed, and I multiply by y, or e to 1/3 x cubed dy dx, plus derivative inside is 3 times 1/3 x squared, so it's just x squared e to 1/3 x cubed times y. And I can go ahead and rearrange this as e to 1/3 x cubed all out front times dy dx plus x squared times y. And this is going to help us solve our ODE. So what's important to note is that d dx of e to integral p of x dx times y is the same thing as e to integral p of x dx times whatever was inside our ODE on the left, which means it's going to be the same as e to integral p of x dx times our ODE on the right. So basically I just said this was the left side of my ODE, So must be equal to if I plugged in the right side, because that's how equations work. That means that d dx of e to integral p of x dx times y is equal to e to integral p of x dx times f of x. I'm just taking this left side and setting it equal to the rightmost side. The middle part is sort of a way for me to connect the two. And this doesn't look like I've done a whole lot yet, but now let's start thinking about setting this up in a way that I could integrate things. So I can move the dx to the other side. Just by rearranging my derivatives. And hit pause if you need to copy some more. Actually, it's okay, I'll just stay here and I'll just write and then what we're going to want to do is we're just going to want to put that integral sign there and integrate both. The integral on the left side looks hard, but because it's d with respect to everything inside it, we actually don't have to evaluate anything. That integral just becomes e to integral p of x dx times y. So I don't have to integrate anything. I just need to be able to calculate e to integral p times y and then write it down. And on the right side, that integral is still a little bit tricky. Who knows what p and f are and how complicated e integral p times f is, but it is something that you could evaluate. And so after you evaluate that integral, you could solve for y is 1 over what's on the left side times the right side. And I'm sorry, I dropped my dx when I came to this side. You do need it over there so you know how to evaluate the integral. And important note, I do not want you to memorize this formula. Like, me showing you this process wasn't because I think that's a cool formula that you should use. I think it's a bad formula that you should never use. I just want you to know that now we can solve for y. So if p and f are defined, but we're trying to find y, which is going to be the case with these linear differential equations, we just need to compute that exponential term. And then integrate some known functions. And so just like we wanted to, we've turned this ODE problem into what's basically a calculus problem. And so hopefully this is kind of showing you how the method works. We're going to do some concrete examples where it's a little easier to follow. And we're going to also go over like a list of steps to solve these problems in the next video.